me share my screen. Okay, so hello,
Yeah, we can
hello.
see you.
Okay, so I cannot see. Like, uh, okay,
Can you move around a few slides so that we check if it's working?
yeah, it's working,
Yeah, yeah, it's working.
but
Okay.
I cannot see the video. So okay,
Video of you. I think you're in
yeah,
full screen mode. That's why you cannot see it. But we can see you and your slides perfectly.
okay. Um, okay, so shall I quit the full screen or it's okay?
No, no, it's better with the full screen. You can carry on.
Okay, so first, I'm Avijit. First of all, I'd like to thank the organizers for giving me this opportunity to present my work. Okay, I'll be talking about nonlinear coherent heat machine. This work has been done with my postdoc mentor, Professor Gerson Kurisky, and Thomas Offertny from Czech Republic and other collaborators. Okay, so here is the plan of the talk. First, I will give a brief overview, and then I'll be talking about work extraction by measurement, following various measurements and effect of noise and photo count in brief. Then I'll discuss what is the problem of measurement-based work extraction and what we can do beyond that. So the answer is we can have a coherent dynamic work extraction, which is autonomous. Then I'll conclude. Okay. So recently, quantum thermodynamics has attracted a great deal of attention. Specifically, the question like to what extent the laws of classical thermodynamics hold in the quantum domain, where one cannot ignore the coherence or entanglement. And it has been found that for state transformation under thermal map or thermalization, classically one needs the free energy gradually decreases. But quantum mechanically, there are other constraints, like there are a set of free energies, infinite number of to be decreased during state transformation. And also there are fundamental questions like can one extract more work and violate the surpass the Carnot bound by expanding quantum resources like entanglement or coherence? The answer is no, and we have shown in some work, previous work, like starting from the maximum entropy principle, it follows that one cannot go beyond the Carnot bound while working with thermal heat reservoir. Okay, but if you are working with heat reservoir which contains coherence or which is squeezed, then one can go, but the usual to temperature heat bath, one cannot go beyond Carnot even exploiting the quantum resources. So the thing is, okay, the quantum laws hold in the quantum domain. There might be some additional restriction, but the traditional laws are there for state transformation or work extraction. So these are some fundamental things which people are curious about, but that field is not only of fundamental interest, it also has some practical importance. So recently there have been several experiments on quantum heat engine with single atom or optical platform. And imagine of a situation like suppose we are doing some quantum information processing task or computation, and there we have enormous heat generation due to this logical irreversibility. And so it will increase the temperature of the quantum system where we do the technological task. So what do you need? We need to cool down the quantum system locally. And this implies that we need efficient refrigerator which can cool down a quantum system locally or in minute scale. And we have to bypass the heat which is produced during the task so that we can utilize the quantum resources, coherence, entanglement in a better way. And also there is other aspect, like when we have heat generation during some work or protocol, can we use this heat to extract work? And why this is important? Recently, it has been shown that in 2020, this classical information and communication technology consumed 11% of the global electricity. So the need of the hour is not only we have quantum protocol which are efficient than the classical ones, but we also need some quantum protocol which are energetically efficient. And that's why when we have heat production, if we can utilize this heat, then it will be helpful as a measure to control the wastage of energy. And also we can cool down the system by utilizing the heat. Okay. So one of the aspect of this work extraction is information engine, which dates back to the Maxwell-Demon thought experiment. I'm not going into the details, but let us take a idealized version of the Maxwell-Demon. Suppose I have a one molecule gas chamber, which is connected to a heat bath. And from thermodynamics second law, I know that we cannot extract work from a single heat bath. But a demon, being an intelligent being, can insert a partition and measure that in which direction of the box, like left or right, the particle is. And depending on this measurement outcome, we can attach a weight and extract work by expanding isothermally the gas molecule. We can extract KT to ln2 amount of work. But there is an apparent violation of the second law because we are extracting work from the heat bath. But the Landauer argument said the second law and said, okay, so if we want to repeat this cycle again, we need to erase the memory of the daemon, and which take KTLN2 amount of work to erase one bit of information. So it is consistent with the second law, but we can have realized measurement engine, and what we can do, we can have the memory at some lower temperature than this temperature. And in principle, there is two heat bath, and we can extract work by measurement. And what is the important thing in measurement engine? We need to know the measurement outcome. Like we need to know whether the particle is on the left side or on the right hand side. And then only we can do some operation based on this measurement outcome, then only we can extract work. So this is the main thing of information engine, which I will be using in the later part. But also notice that in this case, or several measurement engine proposed till date, the entire fraction of the input is used for measurement and to extract information about the working system. So we ask the question, can we bypass this? And we answer this affirmatively in this paper, and then we generalize this for other measurement. But there is one problem with measurement engine. And what is that? We need to do the measurement, and after that, based on the measurement result, we have to do some operation. So inevitably, it is not autonomous. So we need external control to record the measurement result and some performance. So it can be problematic in technological tasks, and that's why the ultimate goal is something if we can do autonomously. So can we do something autonomously? And we answered this question also affirmatively in this thing. Okay, so let us first talk about the measurement-based engine. And one thing, if you have any question, please feel free to stop me and ask. Okay, so what are the basic of this measurement engine, which I'll be talking about? So in this total work, we are considering a thermal input or thermal beam. So it can be a beam of light or it can be a beam of atom. And what we will do, we'll have a beam splitter with high transmittance. So maximum part of this beam passes through, and only a tiny part is used for measurement. And from the measurement result, we can do some feed forward based on operation, and we can extract work just like this scheme. So we do measurement, and then we attach the weight based on the measurement result, whether it is left or right, and then we can extract work. Okay. And what is the main catch here? So we used only a tiny part and we are not measuring the entire part. And we have shown that by doing this measurement on the tiny part, we can still extract almost the entire energy of this input beam, and we can get efficiency close to 1. And the main reason is, like, while we were doing measurement on this very little part, the cost of measurement is also very low. So we don't have to do the erasing or the feed forward based thing on the very tiny part, which minimizes the measurement cost. And that's why uh, we get higher efficiency, which is close to 1. Okay. So in this total talk, what I mean by work extraction. So I think all of you more or less know what is ergotrophy. So ergotrophy is when you can lower the energy of a quantum state by unitary transformation. Okay. And any state whose energy you cannot lower further by unitary transformation, average energy you cannot lower, it's called passive. So any state rho, if you can divide the average energy in two parts. One is the passive part, which cannot be lowered by unitary, and one is the non-passive part, so which is called ergotrophy. And this is like how much energy you can lower by unitary operation. So what is the example of passive state? A thermal state is the example of a passive state. And if we see in the phase space, then we can see that it is centered and the origin, and it falls off monotopically and isotropically. But if we have some distribution which is not falling off monotonically or isotropically, or which is displaced from the origin, we can say it's non-passive. That means it stores some energy which can be extracted by unitary operation. And note that when we are extracting energy with unitary operation, there is no entropy change. So the energy change is only like pure coherent form, which we can say as term, which we can work. And the thing is, the thermal state, though it is passive in initial part, one can do a measurement and render the state non-passive. Okay, so if I represent it pictorially in a phase space, so this is my initial thermal state. Okay, and you can see that it is centered at the origin and falling off monotonically and isotropically. But here you are doing something measurement. In this case, it is phase sensitive homodyne measurement in the tiny part. And by this measurement, I disturb the state on the unmeasured part. So this state in the unmeasured part got displaced from the origin, and it stores some ergotropy, which can be extracted by unitary. So what is the unitary here? Simply bring the state by displacement operator to the origin, and you can extract some work. And here we are doing some standard measurement, which is very common in quantum optics, homodyne measurement, where we estimate the phase quadrature information x and p. And the classical analog of this protocol is if you can estimate the phase of a harmonic oscillator, say pendulum, classical pendulum, and you can stop the pendulum when it is in full swing. And that's why you can release the pendulum and extract the potential energy stored in this pendulum. But the information, phase information is important. If you stop the pendulum here, you cannot extract any work. Okay. One minute. Hello. Hello.
I can hear you.
Yes.
Yeah, so there, I think there is some problem with the connection. Okay. Okay. So schematically, if we say that we have the input thermal distribution, which is like completely disordered, and we cannot extract work solely on this, and we invest some coherent energy or work for measurement, and at the end we get some work, and some part is lost due to detection, and we have the remaining thing. And as we have shown that the post-measure state is displayed, so we can extract the work from displacing the post-measure state again back to the origin and extract some work. Okay, so and by this process we have shown both numerically and analytically with Gaussian approximation that we can have the efficiency which is 1 minus of the order of 1 over square root of bar n. So bar n is the mean input photon number of the beam. And you can see that if you increase this, the efficiency can reach up to 1. So we have done this for both high temperature and low temperature. And it is optimized with respect to the measurement like the local oscillator and the beam splitter transmittivity. And this work we have only extracted by displacement. But there are other operation also, like we can apply other unitary. This post-measure state is also squeezed. So we can do some unsqueezing operation and extract work. But what we have seen that with the increase of input photon number, the percentage of work that can be extracted by squeezing, it reduced. So we can simply extract almost the entire energy by displacement, which is experimentally more feasible. Okay. And also we have considered the practical situation, like we have thermal noise in the unused port of the beam splitter in the optical setup, and we have inefficient detectors. And also sometimes there are dark counts, like there is no photon, but the detector counts something. So we have considered every possible noise. And with the noise also, we have seen like the efficiency, you can always reach the efficiency close to 1 by increasing the input photon number. And here we have also considered the Landau erasing cost and other measurement cost. We have compared with other photonic Maxwell-Demon engine. And in this paper, they have considered a photonic Maxwell-Demon whose maximum efficiency is 1/3. But in our case, as we are measuring a tiny part, we can reach efficiency close to 1. And also we have compared with auto engine, finite time auto engine. And our protocol is 4 times powerful than the auto engine. So we have comparison with other models from information engine and traditional stroke heat engine. I can skip this part depending on time. I don't have much time. Okay, so these are the same protocol, but we consider instead of phase sensitive measurement, if we do photo count. So we just count the number of photons in the beam. And here we have seen the post-measure state. It's not displaced and it's not anisotropic, but it is non-monotonic. So there is a hollow crater in the middle. And if we see in the Fock space distribution, the green dot represents a thermal state, but the post-measure state represents a thermal state, and it is non-passive. So how we can extract work? So here we cannot do displacement or squeezing. Here we need to do permutation in the Fock basis. So which is experimentally very challenging than realizing displacement operator or squeezing. And let us compare the efficiency of this photo count measurement and homodining, the phase sensitive measurement. So if we see that after some input photon number, when it exceeds some value, the efficiency of the photo count is more than the efficiency of the homodining is more than the photo count. So the photo count is experimentally feasible and also efficient. So it's better to use photo count for measurement based engine. Okay, so till now what I have learned that WF, which is work extraction by observation and feed forward, is conceptually simple yet very efficient, and it can surpass the efficiency bound of this auto engine and other information engine proposed till date. But there is one problem, because we need to do the measurement, and the measurement has some cost. And more than that, we need to do some operation based on the measurement outcome. So it is not autonomous. And imagine a situation like there is heat generation during computation or any protocol, and you want to use this heat autonomously. So it is possible. So let us see whether this is possible or not. So suppose I have a hot beam, some hot beams, say a few numbers of hot beam, finite number of hot beams, And I have some cold beams which can be empty state, like if there is nothing, it can be say a cold beam of 0 temperature. And my goal is I will pass the beam through some interferometer. And what I want the energy to concentrate in particular one pre-selected mode. And also I get some this energy in some non-passive form. So the red represent the passive form, like where we cannot extract work by unitary operation, is which these red beams do not store any ergotropy. But what I need, I'll pass this beam to interferometer, and I'll have some non-passive beam in some pre-selected mode, and whose energy is much higher than the individual beam, but keeping the total energy constant. So this is my aim. So is this clear? This part? Look. So okay. So my goal is to concentrate the energy in some pre-selected mode in non-passive form. And what we have shown that if we have linear interferometer, there is no way that we can concentrate the energy in some pre-selected mode. So basically work extraction or concentrating energy in non-passive form in one form is not possible. And also the refrigeration, like if I want to cool down one beam, it's not possible. So what we need nonlinear interferometer. And we have shown that with nonlinear interferometer, we can do this, achieve this feat. And how? So suppose I have some hot beams and I have some cold beams, and there is an interferometry, it's called sampling stage. And then I do some nonlinear feed forward, which is autonomous, unlike the measurement, and I can concentrate the energy in this pre-selected mode. Okay. And what we have shown, the basic building blocks of this scheme, we need 4 modes, like 2 in hot and 2 in cold. And this cold mode can be empty, like which is 0 temperature mode, or it can be at lower temperature than this mode 1 and 4. And then we pass this mode 1 and 4 with a high reflectance beam splitter, where the most of the part is reflected and only tiny part is transmitted, which got mixed up with the cold mode. So these are basically sampling stage. Basically, the cold modes make weak copies of this hot mode. Then we mix these copies in a 50-50 beam splitter. And then in the third stage, what we do, just mode 1 and 2 and mode 3 and 4 are passed through a cross-Kerr nonlinear medium. So what does this cross-Kerr nonlinearity does? Basically, it introduces a phase on this mode, first mode and second mode, depending on the intensity of the mode. So you can see that we get a phase which is depending on the photon numbers of this mode n and m. And what is the Hamiltonian? So this is the Hamiltonian. And after this, if I pass this beam to a phase shifter, pi/2 phase shifter, and mix with a 50-50 beam splitter, we can show that we have energy concentrated in this mode 1, and it got redistribution, and the total energy is constant. Okay. And this is possible only because we have some nonlinear element in this interferometer. So it is not at all possible in the linear framework. Okay. So to explain it in more detail, say in coherent state representation, I have like one coherent state alpha 1 in mode 1 and alpha 4 in this mode 4 with some random phase phi, and I have some empty ports. And in the third stage, in the cross-Kerr stage, what is happened that the first mode got a phase depending on the intensity of the fourth one, and also the fourth one got a phase depending on the intensity of the first one. So you can say this is missing a copy. So as in measurement, we estimate some information, but here in the nonlinear stage, so the first beam got the information of the intensity of the fourth one and vice versa due to this cross-Kerr nonlinearity. And now, after applying this phase shifter and beam splitter, if I calculate the mean intensity in the mode 1 and 4, I got this expression. And I can optimize this with respect to the nonlinear parameter. And what we can show that one can concentrate up to 4/3 of the energy of one input beam in this pre-selected mode. Okay. And if we see the details distribution like photon statistics, then we can see that this is no longer in a thermal form. So it is in some non-passive form where we can extract work by unitary operation. Okay. But the one thing is the efficiency is not so high. So if we can, like, we have two hot modes and we can concentrate the energy 4/3 in this pre-selected mode. But what we can do, that we can apply this scheme again and again. So basically, if we cascade this, like the input of the second is the output from the first two, and we repeat this over again and again. Then what we can see that in this one pre-selected mode, say mode 1, we can have coherent source of energy. And this whole process is autonomous. So we have the beam input beam, and at the output we have some work, and this is possible due to the nonlinear interaction. And if we want to see the nonlinear interaction more mathematically, then how is this possible? So let's say about the two mode, what happens with the mode 1 and 4 in coherent state formalism. So any two mode coherent state can be represented in a Poincare sphere, and Poincare sphere with radius S0, and S0 is the expectation value of this Stokes operator, which is given in terms of the creation and annihilation operator of the modes. And what we have seen that initially the points on the phase space is randomly distributed in this Sx, Sy, and Sj, and this red dot represents a random point. And now in the cross-Kerr stage, this red point is shifted toward the positive hemisphere in the Sy axis. Now in the final step, when we have the phase shifter and the beam splitter, this point is again concentrated in the upper hemisphere of the Sj. So you can see in the nonlinear stage, the points in the phase space got concentrated on this little part. So which is basically we get energy concentration in the pre-selected mode. And we also have detailed quantum analysis, because this coherent state picture is like classical approximation. So if we do detailed quantum analysis, we have this expression, and in the classical limit, we retrieve the result. Okay. And but till now it is theoretical. So can we realize it in experiment? And yes, it is realizable with present day technology. And there are two experimental proposals given by us. One is we have a optical cavity, or say optical resonator, and we have a mechanical resonator. And the mechanical resonator and the optical resonator is coupled by a Josephson qubit. So what can happen? The optical cavity can accumulate a phase which is dependent on the mean number of phonon in the mechanical resonator through the mediation of the Josephson qubit. And another thing we have Rydberg atom, and we can trap the photon in the Rydberg atom, which is called polariton. And with this, they are called then slow photons. And then by dipole-dipole interaction between the Rydberg atom, we can have this cross-Kerr nonlinearity. And this is some scheme which Ofer Fastenberg, one of the co-author of our paper, is doing in his lab, and we are hopeful that we'll have experimental demonstration of this work very soon. Okay, so these are the like work extraction from this beam, but can we use this nonlinearity in some other cases? Yes, we can use this nonlinear interaction for functionalities like transistor, and also non-classical state preparation, preparation of entanglement in optomechanical system. And also we can use this for nonlinear sensing. So one of my collaborators is working in this direction. Okay, so thank you, and please feel free to ask question.
Uh, Thank you. It was a very wonderful talk. Our session is now open for few quick question. So participants can feel free to ask question.
Can I ask questions?
Yes.
Thank you for your talk. First question is how you have displaced, I think, vacuum state to the state squeezed coherent state. You have shown some schematic setup. So
In the first part, the measurement based part?
Yes, theoretically, I can apply displacement operator on the vacuum and get the desired displacement, but you have shown some experimental schema.
No, I'm not applying the displacement operator on the vacuum state.
Okay, so
let me show this again. Okay, so these are the setup. So I have the input beam. Okay, and it's not empty, so it has some mean photon number and a finite temperature. And then on the tiny part, I do the measurement, and the post measure state is automatically got displaced from the input. So I have a thermal input, and if I disturb on this tiny part, and the unmeasured part, which is automatically displaced from the origin.
Thermal
and then
state is all this coherent state, right? With 0 photons or 1 photon? Or...
No. Thermal state is a mixture of coherent state and 0 photon only when it has like 0 temperature thermal state, but it has finite temperature. Like if you have 0 temperature thermal state, basically you don't have any energy, but you need some input energy to extract work.
Yeah, at least one photon or 2 photons in thermal state. Yes, you have, right?
Yeah, so in this homodyne based scheme, you need at least 1 photon on average.
And then you are injecting it by using the coherent state, and coherent state, I understood, if I understood correctly, and then you are mixing with the vacuum state, right?
Yes, so here the coherent state, it's a basis. So any classical state you can write as a mixture of coherent state, right? So here in the picture, so the input can be any noisy input, but as the coherent state is the basis of this, I do the mathematics with coherent state, then I take the probabilistic sum over coherent state. So when I do like thermal state, let me show some slide which I don't present here. So okay, I think I have details. See here, I have this input coherent state. Okay, and then I have like the photon count here, which is related to the quadrature information x and p. Okay, but what I am doing, so I am doing for a coherent state, then my input is a classical mixture of coherent state. So this is the input, and for thermal input, I have this mean photon number, like I can write the distribution in phase with mean photon number n bar, and see that n bar here, it's 1.55, and how the distribution, like when I was doing measurement and photo count, like how this delta nx and delta np, which are the difference in detector count. So we have these pictures, and then what I can do, depending on the measurement outcome, I can have by Bayes rule the distribution of the post measure state, and for different input photon number, I show like how the state are displaced. And like I need, like for this homodyne based work extraction, I need at least 1 photon on average. So if I start with a like empty state, I cannot extract work.
Yes, this is vacuum, and then yes, thermal state, you should have at least 1. Okay.
Yeah, see this, yeah, so see this formula, like this is the general how much work you can extract. So you have 1 minus 1 over square root n. So you need at least 1, otherwise the work is negative.
Yes, yes, yes.
This is for the homodyne, but in photo count, if you have any non-zero photon number, you can extract work in principle.
Final question. When you're talking about cold modes, does it mean that you're talking about vacuum states or thermal state?
It can be vacuum state. So vacuum state basically means a thermal state at 0 temperature, or it can be a thermal distribution at some lower temperature. So in
Okay.
Bin's filter, like if you have empty ports, so basically it empty means okay, so you have a 0 temperature thermal state. Okay, but usually there are thermal noise, so you have to consider this. So that we have, but it is lower temperature than the input.
Okay. And when you're talking about hot states, it means coherent state.
Hot, I mean thermal state. So basically the thermal state is a mixture of coherent state. So it can be coherent state, but what we consider, so I have considered any general state. So coherent state is basically a basis of any non-classical state. So if you do the calculation for coherent state and then you integrate over the input distribution, like this I have the conditional probability for a coherent state alpha, and then I average over all this probability distribution of the input coherent state. And then for this for thermal state we have this distribution. But if we take some state which is other than thermal state, I can do. So coherent state is just a basis. You don't need coherent state.
Yeah,
you can have any noise.
Yeah, you did not find the definition in your presentation regarding hot states. That's why I just asked. Thank you.
Yeah, so actually, yeah, basically, due to time, I skip this because it's can be say like okay, like a beam or a collection of harmonic oscillator, which is a thermal distribution, Gibbs distribution, and it has some mean number of photons. And if the mean number of photons is 0, then means it's 0 temperature, and the temperature is dependent on the mean number of photon. So if you increase the mean number of photon, that means the temperature of the input is more.
Thank you.
Okay, thank you.
So is there any other question? If it is not, then due to running out of time, we are concluding our session over here. And thanks again, Avijit, for your nice presentation. And yeah, our tomorrow session will start from 10 a.m. All participants are requested to attend this session. So yes, we are concluding our session here now.
Thank
See
you.
you tomorrow.
Bye.
Bye.